We're going to spend a few minutes now talking about acid-base equilibria and the Ka values that are associated with those equilibria. Our learning goals include the meaning of pKa, as a variation of Ka, and determining relative acid strengths from pKa values. And then I want to talk about how to determine the pH of a weak acid solution from its Ka value. So let's start by thinking about weak acid equilibria. So remember that a weak acid equilibrium looks like this, where HA is the weak acid and H2O, water, is functioning as the base in this particular reaction. So a proton is transferred from the donor HA to the acceptor H2O to make the conjugate base A- and a hydronium ion. Now the equilibrium constant for this is Ka, and it's defined as the product of the hydronium ion concentration times the conjugate base concentration divided by the undissociated acid. Now we can compare acid strengths by simply comparing values of Ka, and we can begin to see some of the correspondence between those things. But I want to make a special cautionary claim here, and that is that Ka is specific to the combination of the weak acid with water, and it will be different in other solvents. So for example, if you were to run a reaction in a different solvent, you might get a very different sort of equilibrium constant. Let's see if we can understand where that comes from. All right, our weak acid, HA, has a conjugate base A-. Now when we combine it with water, the water is functioning as the base in this reaction and the hydronium ion as its conjugate acid. So the real question is, what happens if we don't have these as the base and the conjugate acid? Let's see what that means at a microscopic level. So when we're talking about this proton transfer, originally the proton is attached to A-, and it might be approached by a water molecule which uses one of its lone non-bonding pairs of electrons to form a new bond to that H. That creates the hydronium ion. When it pulls the proton away, it leaves a negative ion, A- behind it. But that base doesn't have to be water. That base could be something else. And in that case, just a sort of generic base molecule with a pair of non-bonding electrons, that base could come in, grab the proton from the weak acid, leaving the conjugate base of the acid, A-, and forming a different sort of conjugate acid for the base. So if this is what happens, then we could have a very different sort of equilibrium constant. Let me illustrate that with methanol. For example, if we were to take this weak acid and put it into methanol, now the methanol is going to act to remove the proton from the weak acid, and we're going to end up with a protonated methanol molecule, CH3OH2+, which is different from the hydronium ion that we created in the original reaction. And the equilibrium constant for this new reaction doesn't necessarily have to be equal to Ka. Now, generally speaking, we find that acids, the relative strengths of acids, are generally conveyed when we go from one solvent to another, for example. But I want you to be aware of this subtlety, because when we talk about Ka values and everything, we really are talking about reactions that are taking place in an aqueous environment. Now let's talk about the comparative strengths of weak acids based on Ka values. So when we have larger Ka, that means that more hydronium ion will be produced, because remember, the larger the equilibrium constant, the more the reaction tends to the right-hand side. That also means that less of the weak acid will be left intact in the solution. Conversely, the smaller the Ka, the less of the hydronium ion will be produced. So we can draw a direct correlation here that larger Ka values correspond with stronger acids. Now I want to, taking note of the fact that Ka values tend to be over a wide range of magnitudes, and many of them are very small numbers, I want to use the same trick that we did with hydronium ion concentration when we defined pH, and we're going to define a new quantity. I want to define that Ka value is equal to 10 raised to the minus pKa, which is an exponent. And we're going to begin dealing with pKa's as a substitute, at least, for talking about acid strengths. But remember that just as in the case of pH, the smaller the pK value, the stronger the acid. So we're drawing a correlation here that large Ka corresponds to small pKa, just in the same way as large hydronium ion concentrations corresponded to small pH. Let's see if we can make this a little clearer with a picture. So I'm looking at a range of different strengths of acidity. So very strong acids are on the left-hand side of this diagram, and very weak acids are on the right-hand side. And the left-hand side is going to correspond to larger Ka values, so that means things like 10 to the minus 3, for example, would be a large Ka value. That corresponds to a pKa of 3, so large Ka corresponds to small pKa. On the other side, when I have very small acidity, that may correspond to a very weak equilibrium constant. Ka might be as low as something like 10 to the minus 35. That would be an incredibly weak acid, in which case pKa would be equal to 35. So small Ka goes with large pKa, and that also corresponds to very weak acidity. Okay, we want to finish this video with talking about how to get the pH from the Ka value. And it's really no different than solving an equilibrium problem. In fact, we saw a problem like this when we went through equilibrium problems in Module 4. I'm going to use as an example glycolic acid, which is a weak acid that occurs biologically. And this particular weak acid has a Ka value of 1.5 times 10 to the minus 4. This actually makes it a relatively strong weak acid as weak acids go. We're going to imagine that we have a solution that begins with a concentration of glycolic acid that is 0.1 molar. So now to solve for this, I'm going to have to do the same thing I did in the equilibrium module. I'm going to have to set up an ICE table, and you'll notice that I've got the undissociated weak acid on the first column, I've got hydronium ion in the second column, and I've got the conjugate base of the weak acid in the third column. I don't include water in this because, as we know, it does not appear in the equilibrium constant, so we don't need to worry about its concentration. And in any case, this reaction, if it's taking place in water, the water concentration isn't going to change much from beginning to end of this reaction. All right, so now as I fill in the entries in the I row, I'm going to need the initial concentrations. Well, I've only given you one, and that's the concentration of glycolic acid. Typically speaking, in these problems, if I don't give you the concentration, it means it starts off at 0. So that is what it will be for both the hydronium ion and the glycolate conjugate base. Okay, now when we talk about the change, this is the same as we saw before. All of the coefficients in this balanced equation are 1, so the change parameter is going to be negative for the glycolic acid, and it's going to be positive for hydronium ion and the glycolate ion. So we'll have negative x, and plus x. All right, then we just add these two rows together to get the E row. So we'll have equilibrium concentration of the glycolic acid, which would be 0.1 minus x, and the equilibrium concentrations of the hydronium ion and the glycolate ion are both plus x. So now when I set up my equilibrium constant expression, this is what Ka looks like when we write it in terms of concentrations. And now if I substitute in the expressions that I have in the E row of my ICE table, I will see that this equilibrium constant is just equal to x squared divided by 0.1 minus x. I need to solve that equation for x, which again I can do using any sort of mathematical manipulation program, or I can simply solve the quadratic equation. I'm not going to go through that process, but when I do that, I'll find that x, which is, remember, equivalent to the hydronium ion concentration, that's going to equal to 0.00380. Once we have the hydronium ion concentration, then it's a simple matter to convert that to pH, and we're going to use the mathematical definition because that's more direct, but I'll take that 0.00380, I'm going to take the log base 10 of that number, I'm going to multiply it by -1, and when I do that, I will come up with a pH of 2.42. So that would be the pH of this particular glycolic acid solution.